All right. Hello and welcome back to STEM Online Academy. My name is Jason Masterakos. I am the head of the channel. For those who know me, well, there's no need for introduction. You're already subscribers. For new viewers and potential subscribers, I'm I'm a mathematician, right? And mathematician and a physicist actually. And the channel, right? The channel is pretty much about advanced math and physics concepts. For those who about uh, want to learn new topics, uh, or those who are just interested, you could be anybody. You could be an adult learner, an enthusiast, an undergraduate student, um, anything of that nature. And even some graduate students will be interested in my work. Okay. So, what we're going to look at, um, if you've been watching my videos, well, what we mainly do is not just mathematics, math, physics, and AI. We talk about all three of these of these topics, and we go into very interesting detail. Not just the concepts, interesting concepts, but problems too, like problem-solving questions that will get your hair spiked up. Not like Einstein, but anyways. But yeah, we're going to be looking at some very interesting stuff. My model, for those of you who know me, those of you who don't, is to analyze mathematical problems through a logical lens. So what I mean by that is we're going to go through, in particular, uh, in an analysis type of approach. My approach for solving problems, specifically hard problems, which we're going to look at, is by going step one, understanding the problem conceptually. Make sure you understand semantically if it's a word problem or if it's an equation, what you're being asked for. That's very important. Then from there, step two, you want to model the problem, right? You want to make a geometric model of what's going on. That's very important when it comes to mathematics because then you can make sense of the phenomenon and you can make sense of, okay, I'm starting with this this geometric model. This is how it looks like. This is where I need to end up. You compare your model to your computational aspect of the problem, especially in applied mathematics and physics. It's very important to do this approach. Okay, and finally, logically deduce and use mathematical methods, right? Because once you have the model, you can come up with a mathematical equation that you're familiar with, and then you know the method to use. That's the easiest part. Okay, so that's my three pillar approach. All right. So let's get into it. All right. So for those of you who have been watching, the last couple of episodes, seven problems from my new book, Advanced Integration Techniques, looking at mastering advanced integrals, applications, and open-ended problems. All right. So this will be for anybody who is interested in solving, who either wants a real challenge, like this book has a section that is very complicated, it's divided into two aspects. One that is mathematical methods, like learning more mathematical methods on integral calculus, right? That can be applied from calculus 1 to 3, um, vector analysis, complex analysis, numerical analysis, and even applications in quantum physics and stochastic analysis. Okay, and uh, the other part of the book, right, is for those of you who are already know um, integration really well, maybe even integration and measure theory, for those of you who don't know what that is, for those of you who know what that is, and you're ready to look at some really challenging problems in this book, this is the book for you. Okay, there'll be a link in the description where you can get this book. Okay, so let's get into it. So we're going to look at the gamma function visually today. Okay, this is a problem for my book. The gamma function is a very interesting function. Okay, everyone learns factorials. Almost no one knows what factorial really means. Today, we're going to lift that veil. Okay. So, why the gamma function matters in things like analysis and physics. By the way, analysis is this rigorous form of calculus. So why does it matter? The reason why it matters is because the gamma function, okay, first off, I'll talk about physics, right? This can be utilized in quantum physics. Okay, this function right here, I'm going to zoom in on it. Quantum physics, this comes up a lot. Radioactivity, all these types of things. Particle physics. The gamma function is very important in these areas. Okay, a lot of applications. And in analysis, it can pop up in analysis. When it comes to analysis, I don't want to say applications and analysis because it's just mathematics. I don't want to say it's abstract mathematics where physics is applied mathematics. But it pops up in analysis here and there, not as often, but it does pop up. In analysis, we're not really as thing with integral unless you do measure theory and integration. Integration is that's where it will pop up probably a bit more. But yeah. Anyways. All right. So let's look at visualizing this guy right here, x to the n minus 1. I want to talk about visualization in mathematics because it's very important. So let's go here. Okay. All right. So we're going to look at power functions versus the exponential decay. All right. So what we have here, okay, is we have that x to the n minus 1 product part of the gamma function. Okay. Just want you to visualize that. So here it is. All right. We have the function here. And what we're going to see here, the behavior tells us very clearly that this is some sort of exponential growth. Okay, that x to the n minus, or the t to the n minus 1, doesn't matter what I call it, has exponential growth here. All right, so we have exponential growth. Okay, this gives us a very interesting thing to look at. Okay, and then we have exponential decay. Sorry, my graph didn't come out from my simulation for somewhat. Try to visualize for the exponential decay a graph coming asymptotically. Well, not asymptotically. What am I saying? E to the negative x is not asymptotically. It's coming from the left side of the graph and then coming down, right? Coming down along the x-axis. Okay, along the x-axis is asymptotically, right? And if you were to put them together, right, they would just intersect. One going from left to right up. One's going from up from the left and then down to the right. Okay, so that's pretty much how this thing is working. Okay, and you can see that we can vary parameters here. So for instance, n, lambda, animation speed, and anything we want. Okay, so it's pretty cool when you have a simulation like this to work with, and you see how things are working. Okay. All right. Another thing I want to discuss here, this is a very interesting function from my book, okay, is not just the gamma, but deriving a gamma property. And that gamma function property is gamma of n plus 1 equals n times gamma of n. And the way we will do that is we're going to use the gamma function using the regular gamma function. The gamma function, right, is already defined. So the proof will start like this. Gamma of n is equal to the improper integral of x to the n minus 1 times e to the negative x dx. Very straightforward. That's how it's defined. Now, if I'm letting n be n plus 1 because I'm trying to derive gamma of n plus 1, then this is going to be gamma of n plus 1 equals the improper integral of 0 to infinity. Every n will be replaced with n plus 1. So n plus 1, parentheses, minus 1, e to the negative x dx. That will simplify down to the improper integral of x to the n e to the negative x dx. No misunderstandings there. I think that is completely clear. Okay. By the way, as I mentioned, my lectures, you're going to notice some basic form of integral calculus and linear algebra is going to be important for this to understand what I'm saying. And maybe a slight introduction to measure theory. You don't really need measure theory. It'll be good if you do. It's recommended for this book, but those two other topics are mandatory, okay? Calculus and linear algebra is a must. Okay, so we're there, right? Next, we're going to use integration by parts. Let u equal x to the n. That means that my du has to be nx to the n minus 1, the differential. My dv is e to the negative x dx. V is minus e to the negative x, right? All right, so then we have that. Gamma of n plus 1, I'm going to take the limit as t approaches infinity. Why? It's an improper integral, so I have to take the limit. Then we're going to have minus x to the n, e to the negative x, uv, bounded from 0 to 2, 0 to t, sorry, because it's a limit of integration, minus the integral from 0 to t, minus e to the negative x, and x to the n minus 1. There's supposed to be a dx there. My apologies. Dx. Okay, so we have that. Then from here, we have the limit as t approaches infinity of minus x to the n e to the negative x from 0 to t. I can bring up my n into the front of the integral because it's a constant. Integral from 0 to t, x to the n minus 1 e to the negative x dx, right? Next line is going to be limit as t approaches infinity minus t to the n e to the negative t plus n gamma of n, okay? And then from here, you're going to notice that this portion here vanishes. Why? Well, very simple. Let's draw a graph again. See, this is why graphs are very important. Most teachers slash professors, when they do math, they do it abstractly. What's the way I'm doing? But I want to give you a more in-depth, comprehensive understanding of each problem I'm doing. And I feel that doing it graphically is the way to go. So this is my unique approach to this. So if we were to draw e to the negative t, let's say this is a t axis. This is e to the negative t. Okay. As t approaches infinity, right? So watch what happens. So we have e to the negative t. Let's draw that. So that's going to be something like this. That's what I was trying to explain earlier with the graph, exponential decay. As t is approaching, so t is approaching infinity here. So as t approaches infinity, this is approaching 0, right? So as t approaches infinity, then e to the negative t approaches 0. Okay, so that's gone, right? Gone. So I'm left with n gamma of n, and we've just proven that gamma of n plus 1 equals gamma of n, and gamma of n. Okay, I hope that makes sense. All right. So another thing I want to talk about is some other important things here. The gamma function. Well, we're already talking about the gamma function, but we're talking about a property, an interesting property of the gamma function. Okay, so this is going to be gamma of n is equal to n minus 1 factorial. That is a true statement. Okay, gamma of n is equal to n minus 1 all in parentheses factorial. It's related to the factorial. So that's pretty interesting. Okay, now, if you look at gamma, let's look at some examples here. So if you did gamma of n, let's say n is 4, gamma of 4 would be 3 factorial, because n minus 1, 4 minus 1, 3, and then 3 factorial is 6, right? N factorial is always just going down. Just to remind you what n factorial is, n times n minus 1 times n minus 2, so forth, right? Okay. All right, so if we have that, then gamma of 5 is equal to 4 factorial, which is 24, okay? Hope that makes sense. That's an important function to know, right? So if you're finding this level of integration interesting, I am very happy that you are, all right? So now we have the definition, right? So definition, let's go back to the definition. Definition of the gamma function is also equivalent, right? So I mentioned up there, it's equal to two things, either the n minus 1 factorial, or as an integral, the improper integral of x to the z minus 1 e to the negative x dz. Now, why am I putting z here? There is a relationship that I want to talk about with the gamma function that is also important, okay? When it comes to how this extends to real and complex numbers, right? And what you will notice here is that if I let it be z, right? Well, z is usually a plus ib. A is a real number, a b is a complex number. That's what I'm writing in terms of, right? So you could have just put z here being a plus ib, or there's a z, but I didn't put it there. All right. So normally a gamma function integral converges and gives a smooth extension. So here's some special properties, okay, that I want to talk about. The reoccurrence property, okay? The reoccurrence property states that if you have gamma of z plus 1, where z is a complex number, is equal to the complex number z times gamma of z, okay? And the special values of this, so we can apply this logic very straightforward. Gamma of 1 would be 0 factorial, okay? There's a 0 factorial. 0 factorial has to automatically be 1, right? 0 factorial is 1. Gamma of 1/2 would be root pi. Gamma of 3/2 would be root pi over 2. And you can figure out the pattern, right? Every time I would have a gamma of z plus 1. Okay, try and figure out what the next ones are. That's your homework. If you had gamma of 5 over 2, right? What would that be? Gamma of so forth, gamma of 7 over 2, doesn't matter, right? And this keeps going. Okay, I want you to do these ones for homework. I want you guys, the audience, to engage with me, okay? All right, so we have that. Okay, so we have these guys right here. Okay, all right, so we have that. And there's something else I would like to talk about. One last thing is pretty much the applications of this. As I mentioned, the physical applications are immense, right? Physical applications, entropy, partitions. What I mean by entropy, first off, has to do with thermodynamics, for those of you who are in physics or interested in physics. Partition functions, that's in, again, thermodynamics. And path integrals in quantum physics as well. This is applied a lot. Okay, so all those areas, that is very, very important. So that's the end of my talk today, my usual talks. I usually try to come on 3 times a week. Lately it's been 2. I'm going to go 3, then I'm going to make it even more. Okay, I'm going to come on pretty often. Okay, because I want to make sure you guys are understanding these topics to a very deep degree. Okay, all right. So if you want more integrals like this, my book teaches all this, and it's very structured. It's very structured, and it progresses slowly in difficulty from the very basics to the very complex. You don't even have to finish this book. It's probably not even finishable, but um, it's for all different audiences, as I mentioned, right? Whether you're an undergraduate, graduate student, or adult learner who's just going back to school, finishing calculus, going to university, this is the book for you. Okay. So I hope you will like and subscribe to the channel. There will be plenty of more interesting problems from my book. As I said, problems, topics, anything. We'll discuss all that. Also, if you have anything in the chat that you want to discuss, please go in the chat. I am always free to discuss something. Do you have want help in? If you want more things on my book, more you can ask me anything about my book, tutoring, consulting, whatever it is. I'm the guy for that. All right. Have a wonderful day and see you guys next time. Bye bye.